Hey everybody, it's Dr. Duncan here. We've covered a lot of ground in understanding the role of competition in ecosystems, but we still have a few important concepts to cover before we're done. You should watch this screencast after you've watched the videos on constructing and understanding Zinjis. Competition, as you recall, is the most common form of species interaction, and it's had tremendous influence on our ecosystems. We've already seen a few examples of this. Recall the results of the experiments done by Gauss, who examined how three species of paramecia performed when matched against one another. Gauss found that when Caudatum was matched against Aurelia, Aurelia would always win. You see that in the lower left here. But when Caudatum was matched against Bursaria, Bursaria and Caudatum would coexist. And of course here you should be thinking about those Zinjis and how the Zinjis relate to these outcomes. Another example we've already seen was with barnacle species growing on the rocky Pacific coast in the intertidal zone. It was found through experimentation that the larger species, Semibalanus, had a competitive advantage at the deeper levels, and it would outcompete Chithalmus, the smaller species. Semibalanus had a more narrow niche, however, and Chithalmus was able to survive at the upper elevations where Semibalanus could not. Using our new concepts, we would say that the lower elevations are a zone of competitive exclusion for Chithalmus. However, in the greater ecosystem of the entire rocky intertidal zone, the two species coexist. All this to say that you must specify the context in which you apply these new concepts. One of the impacts of competition is that it causes there to be limited similarity among species that compete for a resource. Here we see two species that use the same category of resource, but they each use a different range of those resources, and so they don't compete. In fact, there's enough empty niche space in the ecosystem that we can add a third species. There's some overlap between the new species and its neighbor, but not enough for competition exclusion to occur. However, if we were to try to add more species, we'd find that there's not enough room. All the available resources were already spoken for. Here we have another example. The bluegill, the green sunfish, and the pumpkin seed are all in the sunfish family. They're very similar. And when they live in ponds without the other species, each prefers to hang out in the weeds where they can hide from predators and also find an abundance of prey. However, when all three species are forced to live together through experimentation, each segregates into different zones of the ecosystem. Here the green sunfish gets the weeds because it's the most aggressive of the three species. This is very similar to the barnacle example. One of the big challenges in evolutionary ecology is determining the degree to which behaviors and other traits we see today have been influenced by evolution in the past. One of the predictions is that in situations where there are many species competing for a resource, we'd see the compression or the shrinking of niches as more species inhabit an ecosystem and compete for similar resources. At the left, we have just 3 species sharing a resource gradient. But when instead we have 5 species in the same ecosystem, as you see to the right, we'd expect that the niches of the species would have to become compressed as they evolve traits to exploit resources not used by other species to avoid competition. There are countless examples where this appears to be the case from ecosystems around the world. This cartoon illustrates just one of many studies comparing niche differentiation among other species. In this case, small lizards known as anoles. All anoles eat the same resource, small bugs, but instead of just one species, there are 7 that inhabit this ecosystem. Each lives in a microhabitat that isn't used by the others. This strongly suggests that evolution has shaped the tendencies of these species to use these different habitats, and has also likely shaped the body form of these species. Note the species in the picture at the top left has a more agile body form with which it runs down prey from low perches. The canopy-dwelling species seen at the top right is slow-moving and blends in with the branches on which it waits. it ambushes prey that don't see it. These sorts of patterns strongly suggest that competition has been a very strong force in the evolution of these species. Even stronger proof of this comes from situations where two competing species from an ecosystem also live in different areas where the other species is absent. In this example, we're looking at two species of finches from the Galapagos Islands. At the top, we see that only G. fuliginosa lives on Los Hermanos Islets, while in the middle panel, we see that G. fortis lives only on Daphne Major, another island. When these species are living separately, or as we say, allopatrically, they have very similar beak depths as indicated by the graphs. But as we see in the bottom panel, on San Cristobal and Flaviana Islands, the two species live together, or sympatrically. Notice that on these islands, the two finch species have very different beak depths. Presumably, it is competition that has shaped beak size on these islands where the species are living sympatrically. Instances where competition has caused a shift in characteristics, such as beak shape, are known in evolutionary biology as character displacement. All right, that's a wrap. If any of these concepts are a little unclear to you, be sure to reach out to your instructor.